All right, let's get started here. Thank you for joining us this morning. We are here to talk to you about the Facility Infection Risk Estimator and how it's been put to use since its debut in June. We want this next hour to be interactive, and we have a fairly small group, so please submit a lot of questions and comments, and let's make this more of a discussion rather than a presentation. My name is Dannie DiIonno, and I'll be presenting today along with Marcel, Harmon, and Pete Jefferson. After reviewing the attendee list, it's clear that most of you have seen us present before or know us personally. Therefore, instead of reading our bios, I'll provide a fun fact about each presenter. First, Marcel Harmon is a senior associate and runs our research and development team. He and his wife used to practice martial arts pre-kids. On a trip to China, he had the honor of performing a northern Shaolin Kwando form in the courtyard of the Purple Cloud Palace complex on Wudong Mountain in Hebei Province, China. He almost fell on his face performing in front of several masters, a grandmaster, and students from the US and China. Good times. Pete is the principal and is the practice lead for the building science team. As a kid, Pete missed out on a trip to the National Geographic Bee in Washington, D.C. by one question. To this day, he will never forget that an anemometer is the instrument used to measure wind speed. And finally, I'm a senior associate and the Net Zero Advocacy Manager on the building science team. My fun fact is that in college, I wrote my honors thesis about how concert goers of different genres have different behaviors in regards to environmental stewardship. It was one of the first studies that looked at musical interest in relation to environmental behaviors, and it earned me high honors status. Our name is inspired by the natural environment and how we use the natural environment to influence our design. Throughout our firm's history, our purpose has been improving life through better built environments. This is our mantra, and we use this message to influence everything we do. Our beliefs are rooted in nature, which has taught us that true sustainability sits at the intersection of human experience and environmental stewardship. These are the AIA learning objectives for today's presentation. At the end of this webinar, you should know how to put the tool to use and know which scenarios would be a good application for this tool. All right, here's the agenda. We'll do an extremely brief overview of the tool, and then we will dive into our 4 case studies: a church in Pittsburgh, a school district in Colorado, a university in Florida, another school district in Kansas. And due to the nature of what this tool kind of reveals about the space, most of our clients are asking us to remain confidential, but I promise that these are real clients that we've helped in these scenarios. We're hoping to leave a lot of time for open discussion and Q&A, and then if we do have time at the end, we can do a couple other case studies. All right, really quickly, I probably threw this in without you knowing, Marcel. I just wanted to go over how you can access the tool. So if you just go to BranchPattern.com and then click on the little menu circle in the top right corner, you can find the direct link to the tool under the research category. There are 3 places to input information about the building, and then you scroll down to see the results. So you need some demographics and room info, some viral parameter information, and then you enter a baseline and design condition to get a comparison for how the virus will be transmitted indoors. We did do a webinar just last Wednesday, and that is on YouTube. So once I'm done talking, I'll put a link to that in the chat. But that's a great deep dive into all of the inputs and outputs. So I suggest you look that up if you're having trouble. All right, our first case study is a church in Pittsburgh. Pete is a member of this church and was asked by his pastor to help get him understand how to reopen in-person services safely. Many people have struggled without a place of worship or a place to gather, but modeling the return to a church is also a good proxy for modeling other gathering places with a lot of people talking and singing. For example, these strategies could also apply to an indoor concert or maybe even a political rally. So Pete will share how he used the Facility Infection Risk Estimator to help his church reopen in-person services.
Yeah, thanks, Danny. So what you're actually seeing there was an article that ran in the Pittsburgh Post-Gazette a few weeks ago that talked about the work that we did with a couple churches here using the tool. And worship spaces are really interesting in general for a lot of reasons. And keep in mind that a lot of congregations have been going to outdoor worship over the last few months. So as weather starts to get cooler, there's there's an interest in returning indoors, but most don't really know the quality of the space and how safe it is. Churches present kind of some interesting problems in general going into it. Most churches are not well funded, to put it lightly. So as a result of not really having much in way of means, you see a lot of dated facilities, systems that are band-aided and glued together and barely holding on. So this notion of then putting a bunch of people into a space, filling up the pews, which is normally what churches want to have happen, that's at odds with what we know is the right thing to be doing right now. So in this particular case, my own personal church came to me, of course, you know, once they knew what I did, you get roped into things like being on a church's COVID task force, and then helping out with it too. And because church pastors talk to one another, that sort of led to wider application of this analysis at a couple other churches too. So while the images of my church, the church that I go to actually was in much better shape than the analysis that we'll walk you through, in part because we had mechanical systems there. And that's a big thing right off the bat. So Dannie, if you want to go to the next slide, I'll kind of set the scene here for it. So I was asked by another church shortly after having done this one for my own to come in and help them look at their spaces. They were actually interested in understanding the quality of two different spaces in the building. One, the sanctuary where they would normally have worship, and two, the fellowship hall. You know, they knew enough to know that the fellowship hall being a bigger space might be safer, but they didn't have really any context for what that meant in the grand scheme of things. So in previous webinars, we've talked about how to use the tool in some detail. I'm going to focus a little bit more on the parameters that we modeled, because each facility type is so different. And I think what's also interesting about churches is what we found is it's really more behavior based than just about anything. Whereas a lot of facilities were focused on environmental conditions, in churches, we're going to talk about things like singing and mask wearing, because those are where we saw the biggest impact on things. So using the tool, we essentially defined the box. In this case, the sanctuary is 2,300 square feet, 14-foot high ceiling height. Then we define the number of people in the box. They can typically hold much more than what we modeled for, but that's not the reality of a typical Sunday service anymore, especially not in 2020. You know, most of the outdoor services were somewhere around 40, 45 people. So we modeled it with 50 just to be a little bit cautious. Then we have to model another parameter too, which is the duration, the exposure time there. The longer we are in spaces with a potentially infected person, the more dangerous the situation is. So then this became sort of a criteria that we had to challenge pastors with. So when they say that they're going to keep service down to under an hour, now it starts to really have some consequences if they run long. So we modeled it for 1 hour. In this particular case, a lot of times when we model schools, and you'll see some of that, we'll model it for one potentially infected person. In the case of a church, we model it for two, because we thought if it was a couple of spouses, they came to church, they could potentially be infected together. And because it's coming up on winter, we wanted to model future winter conditions. Now, in this particular church, unfortunately, neither of these spaces had a mechanical system that would bring in outside air. They both have operable windows, but that's not something that one can really rely on consistently for good airflow. So most of the time, we're just modeling zero outside air when we get into those types of spaces. So what we did is we established a baseline. If you're familiar with energy modeling, that's sort of how we approach it there. And baseline is kind of what is. But I also wanted to put ourselves in the shoes of a congregationalist who might be asking a lot of questions like, why do we have to wear masks? Why are we not allowed to sing? So when we got to modeling some of these scenarios, that's what we did. We wanted to sort of answer those questions before they were even asked. So you can see the parameters here, the baseline. We tried to model really as the space as it exists with normal worship happening, and then set up some criteria for speaking versus singing and just breathing. One of the things that we have developed in version 2 of the tool is different expiratory means. That's what those things are, speaking versus breathing. And there's a huge difference in terms of viral load based on that. So we wanted to model those scenarios. So then we looked at strategy number 1, the simplest strategy that represents a form of change there. So we ask 100% of the attendees to wear masks, but they still kind of have a normal worship practice there. In this case, that would be speaking loudly or singing. Now, in reality, we understand that a typical service is sort of a mix of those things. It's usually not singing for 60 minutes there, unless it's like a Christmas mass, but it sets a scenario for us, maybe one end of the spectrum there to look at. So then strategy number 2, wear masks, but then just change it to speaking. So a little bit more just conversational. And then strategy number 3, 100% of the attendees wear masks. We go to speaking, and then we looked at adding 4 HEPA air purifiers in the space too. And these things range from about $200 to $400 a piece. So for a church, it's still an investment, but in the grand scheme of things, a pretty minor investment. So those were the scenarios that we laid out for it. So you can go to the next slide, Danny, and we'll talk about the results. So the first one, baseline, the space as it currently exists, you put 50 people in there and you have them sing for an hour. And it's almost a near certainty that with 2 people infected, at the end of that, almost everybody would come away infected on it. That is obviously really shocking, but it actually, there's some parallels with some super spreader events out there, including the Skagit Washington choir there. So, this practice of coming in and singing for an hour is especially dangerous in a church, even one that is ventilated. We've seen that, but especially one that's not ventilated. And so you can see the different parameters as they were laid out there. Ultimately, this church, for about $1,000 of investment in HEPA filters and changing behavior, was able to significantly lower the risk. In fact, the pastor of my own church took this meme from Japan, this amusement park where they're asking people that ride roller coasters now to scream inside their hearts instead of screaming out loud. He's essentially asking Congregationalists to sing inside their hearts instead of singing out loud too. So that's how he was able to make the pitch. So this is how the sanctuary modeled. If you go to the next slide, Danny, we ran the same scenario for the fellowship hall. In this particular case, it was a bigger box, and that was really the main thing going for it. It's a little bit bigger square footage, higher ceilings, but essentially the same scenarios, no mechanical ventilation. So that's a concern as well. And so if you kind of move to the results, Danny, what you'll see is it was safer. We don't have them side by side, but if we did, you would see that the fellowship hall is a safer space. The probability of infection is lower in each of these scenarios. But ultimately, when you get to the strategy number 3, the full combination of scenarios, they were both so low that the general guidance back to them was use the space that allows you to enforce social distancing the best. So for them, that really is the sanctuary space. They can sort of rope off pews, have families that ride together in a car, sit together, as opposed to a big open space like a fellowship hall where it's just maybe a free-for-all with chairs. So one question somebody's asked me before too is how long did this analysis take? And that's kind of the beauty of the FIRE tool here, the Facility Infection Risk Estimator. It took about 1 hour on site to assess the systems. It helps that they didn't have much in the way of systems to assess, so that went pretty fast. And then it was about an hour or 2 hours of running the calculations, different scenarios, and putting it together in some results that could be presented to the congregation. So you're talking about maybe 3 hours of effort there, and then the church spent about $1,000 on HEPA filters, not counting the cost of little masks. So that was the church scenario. In a couple weeks, I think I'll be doing a Zoom call with a whole bunch of churches in Western Pennsylvania, because I think this has gotten out a little bit, and more interested in doing some of these assessments too. So, really pleased to see how this tool can help a lot of people out there. So that's the first case study.
Thanks. And before we move on, I thought it might be nice to sprinkle in questions as they come in. So John asked, baseline breathing is still fairly high, about 50% for the church example. Are there reasons for this? Is it down to airflow assumptions?
Yeah, so in this case, so the baseline again is like normal operation of the space. So they don't have mechanical ventilation in it, which is a problem. By not having mechanical ventilation, they actually don't even have filtration either. So it's just a bunch of hot water radiators in the space there. So the probability of infection is really high because it would be 50 people without masks in an enclosed space, breathing there for an hour. And that's a fairly dangerous situation, especially with two people there. So that's one of the reasons that worked out that way. And you can see when you switch, strategy number one is essentially just asking people to wear masks, and they're still allowed to sing, even though that's not what we would recommend. So in this particular case, without having any sort of mechanical systems, behavior affects it a lot, and masks are really important here. So we can actually model even a lower utilization of the masks too. So, I think we modeled this at 100% of attendees wearing masks, but if you wanted to model some cheaters in there too, you could.
Great, and one more question for this one, and then I'll ask the other question kind of later on. Is the location of HEPA filters taken into consideration, or is that too detailed?
Yeah, so it's not taken into consideration in the model itself. So the model itself relies on essentially a well-mixed space, and that's where some engineering judgment comes into play in terms of how many HEPA filters could actually do that well. So in this case, it was 4 positioned uniformly throughout the space, but the tool itself doesn't do that. We don't get to the level of computational fluid dynamics in it. So that is one of those things where, yeah, if you just stuck four HEPA air purifiers in a corner all next to each other, that's not going to actually work the way it's being modeled there. So you do have to consider that. And I see one other question about larger churches having mechanical ventilation. That's absolutely true. Those are actually harder to model, but what you want to have in your space, absolutely. And so if they have, what I found with the churches is most churches either, if they don't have somebody in-house that is a mechanical expert, they usually contract with a mechanical contractor that helps provide service. And so if that person can be engaged in some of the analysis and provide information about like how much outside air is brought into this air handler, that's a big help in being able to fill in some of the data.
Great, thank you. Okay, so our next case study is a school district in Colorado. We have been working with this district on another project, and they've known us for a while. They're familiar with our work and our commitment to healthy indoor spaces. So we were engaged to help the facilities team make conscious decisions on return to school and how they can spend bond dollars on deferred maintenance projects.
Yeah, so I'll tackle this one too. We do a lot of work in the K-12 sector, and what you see on the right here is an all too common scenario. This is a school district that has a pretty robust facilities management team, but like all school districts are stretched thin, especially this one's a growing school district. So what we see going into a lot of school projects, I've shared this in some other webinars, but on average nationally, about 70 to 90% of K-12 projects are underventilated when compared to ASHRAE standards for it. And that's in operation, but we also see that in design. We see that out in the field with things like this. And so, one of the things I always, I've been a little frustrated about over the last 6-7 months is that when people talk about crowded, indoor, poorly ventilated spaces, and then the news cuts to a scene of a bar or a restaurant, I want to sort of holler that we need to talk about schools too, because that's the reality of the situation. And so in this particular school district, I think right around 50,000 students there, we looked at a half dozen schools that are essentially prototypes and very similar to the other 65 or so schools in the district. So yeah, if you go to the next slide, Danny, I'll talk a little bit more about that. I mentioned that schools struggle to meet ventilation. We have this really large problem in the industry for some reason of designers not designing to ASHRAE 62.1. I'm not entirely sure why that happens. I have a couple different hypotheses on it, but when we looked at the plans for these schools, and these are 6 classrooms in 6 different schools there, so we couldn't analyze every single classroom in every single school, given the time that we had to work with the school district and help them assess it. But out of the 6 schools that we studied, 5 failed to meet ASHRAE 62 standards in design. So just going into it, even if the systems worked the way they were designed, they would be short. And some of them were woefully short. One classroom, for example, had enough outside air in the design that per code should have only been 7 students occupying it. And on average, they're putting about 27, 28 students in there. So that's an issue right off the bat. We laid out the parameters. These are some of the toughest systems, I will say, to model, though, variable air volume systems, because they're dynamic, they're constantly changing, and how they operate in the summer is totally different than how they operate in the winter. So to use the tool and apply that, we do have to sort of pick a point in time as we move to winter here, lower levels of humidity, and essentially more in-person classes happening. What we're modeling is really more of like winter design conditions. So we maybe haven't hit it fully, but we're getting there. So we looked at the model a couple different ways with existing systems here. One of the easy changes to move to was 100% mask wearing. Most schools have done that. And harder change is MERV level filters there. So you can't just throw higher level MERV filters in there thoughtlessly. So that's something that on a school by school basis has to be studied to see if air handling systems can handle it. And if they can, great. So that became the second bundle here, which we're lumping under design 2. So move to 100% mask wearing, and then fix the ventilation systems, try to get those to a level that's compliant with ASHRAE 62. And then add those MERV 13 filters. So you can see the parameters that we modeled for. It's essentially a typical classroom with 1 infected person in the space. So you can go ahead to the next slide, Danny. So here's the results. And again, expiratory means matters a lot. Whether it is just sitting there breathing, obviously a teacher's going to be speaking, but not all 25 or 30 kids in a space at the same time for the whole duration, versus just breathing. And we model both of these because it's typically not an either or scenario. Reality is somewhere in between. So a teacher may be lecturing for a while and then there's some group conversation, but it's not all of the occupants. I should say that the speaking scenario represents all of the occupants in the space speaking for the entire duration of time there. So reality is probably closer to the breathing probability of infection here. So this is the baseline with how things work as currently built there. So the next one would be with the design, the first bundle of options there, which was the mask wearing. And I'm trying to recall, Danny, can hang on one second. So mask wearing and still the MERV 7 filters. I was trying to remember which filtration we had there. My apologies. So you can see the mask wearing makes a pretty significant difference there. And then if you go to the next set of outcomes, that's the mask wearing plus improving the ventilation system there and moving to MERV 13 filter. So, if we modeled the ventilation and filters first, and then left masks there, you'd see a pretty significant change with the ventilation and filter. So you see sort of like a smaller change there in the design 2 package because we've already assumed mask wearing in this there. So one question that comes up a lot is what's more important, mask wearing or ventilation and filtration? And the answer is yes. It's all of those things. And so what sort of presents as the most important kind of depends on which you model first and if you break them out individually as strategies there too. So as you can see, going from the baseline to the full set of strategies there, in the first classroom, it lowers it by about half. The second classroom, you're beyond a half, it's almost a third of the risk there. So these things matter. They're really important. The biggest thing that I found and take away with schools is we really have to get systems working at least the way they were designed, but preferably preferably better than most of the designs, because so many designs are deficient there. So.
And I will say, I know in this example too, a community member asked, what are you doing to make the classroom safer for my child? And to show these graphs to say, these are the strategies we've done, and this is how we've lowered probability of infection is really important.
Yeah. So Danny, and you can just put all of them up at the same time. So what we were talking before was probability of infection with these different scenarios. What if you actually translate that to number of people? So the tool is able to do that. So sometimes it's helpful to think that way, because these are real people that go into these buildings. So, versus talking about percentages and probabilities, essentially going from potentially 3.6, so that's either 3 or 4 in reality, to 1.9. So about 2 people, you've cut it in half. And then if you extrapolate that out across the entire school, and a school might have 15, 20 classrooms in it, that's a lot of people. Now, you're not going to have, in all likelihood, an infected person in every single classroom at the same time there. But there could be one in one classroom or multiple classrooms. So sometimes this can be a helpful way to look at the same sort of information too. And the tool provides that. So yeah, this is at full occupancy. And then just our last slide here too. You can share that. So one strategy that school districts have done is gone to half occupancy. And so, of course, with half the people in there, the risk is about halved. So that's kind of the other takeaway of it. So that's the school case study.
Great, thanks, Pete.
There is a little.
Sure.
Oh.
So, yeah, there is a little more to it.
Okay. Yeah.
So, if we so everything up to this point was you're assuming somebody is infected in the space, right? But there's the other half of it that is important to consider is what's the likelihood that somebody is actually infected in your space, and that depends on lots of factors, primarily your community infection rate. And so you can take a look at your local county data to get at least an idea of what that might be, maybe even working with them if you really want to take this into account. But typically most counties will report like the number of cases per 100,000 individuals, which you can translate to the low end of what the likelihood or what the infection rate is, and then also look at a percent positivity rate. So that's the percent of individuals that are actually infected who actually get tested, and that's at the high end, and it's likely overestimating it. So in this particular case, looking at this Associated County at the time that we looked at it, it was that range is 0.3% to 8% roughly is the infection rate within the community. It's somewhere in there. It's probably closer to the 0.3 than the 8. So if you just assume a 1.25, and this is where talking to your county health department to get a better handle of what that assumption should be. If you really want to do this, is something that you might want to consider. But if you assume the 1.25% infection rate within the community, and then you look at the different occupancies for each of the classrooms, you can calculate what the probability is of having somebody that's actually infected within the space. And that's what those percentages listed to each occupancy level are all the way across. And so then you take that number, you multiply that by your probability of infection that we calculated previously, and that's your total risk on any given day, assuming that that's your infection county or community infection rate of 1.25% and the environmental conditions that we input within the model. And so then you can also multiply that by the occupancy to get an idea of what potentially the number of infected people would be, considering the total risk, not just the probability of infection. And of course, you see it goes down, obviously, from that perspective. At least towards the breathing in, we're starting to get below that one additional infected person, and it just keeps going down as you start implementing mask wearing and then making the improvements to the ventilation and filtration. Even once you do that, even the high end of speaking starts to get down to where you want it to be. And then if you have half occupancy, obviously much lower, and you can actually feel not too bad. And obviously, as your community infection rates rise, those will also rise. But That's why it's important to keep community infection rates low. But if you doing some basic measures like mask wearing and improving ventilation, taking into account your community spread rates, you can, if you're actually being mindful about it, you can feel somewhat confident that you limited your risk of infection. The other thing to notice is that as we went through all that data, originally there was a lot of disparity, inequities among the classroom risks. As you start implementing procedures, that inequity starts to go down, which is an important thing to consider as well. In a school district, you don't want to have inequities among your classrooms or among your schools in terms of the risk being presented.
We do have a question about community and test rates of infection, asking if the estimator if the guide provides this as a suggestion for using the estimator. And just commenting that the component drives a large part of the risk, which is true.
It's true. Currently, the guide does not have this in there. I thought about adding it. It's something that we could add to help people walk through it, but it's also something that you really need to not just look at the data, but probably talk to your county health department individuals as well to make sure you're using what they would consider the most accurate estimate for that is. And the thing is, it can change. It can fluctuate quite a bit day to day even. That's why those 14-day rolling averages help minimize that. But it's something you would need to keep track of.
And yeah, what we talked about last week is this: if you have 0 infected people in your space, then this tool will spit out some funny looking results because then there's no probability of infection. So trying to figure out what is the probability that someone even is infected is definitely part of this conversation that we're having. But as Marcel noted, the more cases go up in our communities, the more likely it will be that 1 person or 2 people are infected in these larger spaces. And then we do have a couple questions we can hit on really quickly before moving on to the next case study. This one says, clearly, which strategy you recommend first has an effect on your marginal POI saving, especially when giving a cost and risk reduction. So does this affect recommendations or design strategy? And one.
Yes. Oh, so I was just going to hit on that because, oh, well, why don't you go ahead with the follow-up because it's related.
Well, yeah, I was actually just going to talk about that question, but I'll let you answer that. So then the next one is, would you recommend HEPA filters first at high cost, but doing first would have larger percentage decrease in potential, what does it say? And then masks at lower cost, but the percentage decrease would be less as HEPA filters are already reducing risk.
Yeah, so this is picking up on what I pointed out there, that the order of strategies that you present matters. And for some people on this call, they might be more familiar with energy modeling than modeling for health outcomes here. And so there are parallels with energy modeling from the standpoint of, say, I have a baseline code compliant model, and then I model a bunch of envelope upgrades, so better insulation, all of those things, and I've cut the energy use in half for that building. Well, then what's left over for a mechanical system to do is much smaller. So then if I model the mechanical system, it might only show a 5% savings, instead of if I started with that, it shows a 20% savings. So in doing these strategies, if you want to assess each strategy on its own, you can do that. It's just more runs, more iterations of the runs there. So you could have a baseline and then a scenario where all you do is masks, a baseline and a scenario where all you do is upgrade the filters. In terms of what I presented, I took some liberties there by starting with masks. Yeah, not just because it's a low cost thing, but talking with both pastors of both churches, that was already an expected norm and behavior that they were really comfortable with asking people to do. So then the question becomes, okay, do we need to, you start with that, and then by the time you get to HEPA filters, the question is, do we need to spend $1,000 or on this? Or if it's a school district, do we need to incur the cost of improved filters and the energy use that is associated with that too? So yeah, so with most of these, we're starting with masks because that's already part of their behavior. But if you had somebody that was challenging the notion of why masks are required, you can isolate that on its own and look at that type of situation there. So for each user of this, you have to sort of decide how many different strategies do you want to model individually, because that can add to the work significantly.
Great, thank you. Okay, so our third case study here is now a university conference room that was turned into an open office. So one of the exciting attributes of this tool is that in the first two case studies, the people who engaged us in conversation already knew who we were, where this was kind of a call out of the blue that came after we launched the free online version of the tool. And we were asked by a university to help them model a specific room in their facilities building. And what they did was they converted a medium-sized conference room to an open office where 10 people were working for 8 or more hours a day before the pandemic. And they wanted to know how many people could be back in the office and for how long, and using our tool to figure that out. So we helped them model this scenario. You can go to the next slide, thanks. So 400 square feet with 9-foot ceilings, 90 CFM of outdoor air and 500 CFM of recirculated air, 40% humidity with MERV 7 filters, and 1 infected person speaking as a medium shutter. So they knew that they would be wearing masks, so that kind of answers this last question. So the baseline was just wearing masks in this space, but they wanted to know how many people could they put back into the room and for how long, and what was the appropriate maximum occupancy and maximum exposure time. And then we also modeled adding 1 portable air cleaning unit. So here are the results, and you can see the along the top here is hours of exposure, and then along the side is number of employees. And the chart at the top is just wearing masks, and the second graph is adding that portable air cleaning unit. And these numbers are representing the number of people who would leave infected based on the percentage of probability of infection. And so the first graph here, you see this like black line kind of stair-stepping through the graph. And that black line represents where the cutoff is that more than 1 person would leave infected. And so you can see this circled red number here is less than half. So it's likely that less than half of a person, so close to 0, are going to leave infected. And that was at 2 employees for 4 hours a day. But if we added this portable air cleaning unit, you see these numbers drastically change. So for that same probability of infection, 0.4, now you can get 10 people in the space for 2 hours or 4 people in the space for 5 hours. So we know not all spaces are being used the way they were originally designed for. We see that all the time. So a conference room being used as a small open office isn't very uncommon. And so you can use the tool to get a sense of how the probability of infection varies in the space based on the hours of exposure and the number of people, in addition to these mechanical alterations. And we can't necessarily advise you on what's safe enough or not safe enough, but we can show you the numbers and help you make that decision that's best for your building occupants and what you're comfortable with. You can also use this same application for conference rooms. I know that even in our own offices, we're wondering how many people can safely have a meeting together in a conference room. So the same kind of strategy can apply. Okay, we have one more case study here, which is in a school district in the KC area. And then after this case study, we will move into a discussion and Q&A section. So please get your questions, and I know we've been answering them throughout the presentation as well. So Marcel, I'll let you take it away here.
Great. Okay, so one of the things that we're seeing with school districts, and even more than just school districts, universities, even offices, is occupants kind of, they have their own concerns about how safe the buildings are that they're going to be in. And certainly in the case of schools, we know that there are students, there are parents, there are teachers that are purchasing CO2 monitors to take in and get an understanding of how safe their building is relative to the amount, using that as a proxy for the ventilation that's coming in, and how can we at least have an understanding of what's going on, and maybe even use that data to talk to facilities or the board or somebody to help, make sure that we're making improvements and making spaces as safe as possible. And we're even seeing teachers, physics teachers and other science teachers use this as part of their curriculum and using it as part of the lessons that they're planning and engaging with researchers on Twitter to help them work through some of these questions. So I've got an acquaintance, friend of mine in Kansas City, who purchased one of these and had his daughter take it into their high school and was taking some measurements in class, and he sent me the data, and I was like, well, what can we do with that? Can we take a look at it, or take a run with that and do the calculator and see what happens? So here's one of the outputs from the CO2 monitoring here, from a couple different classes. I focused on the stats is the one that he asked me about specifically. And at the time, I think for that particular day, there were 6 people in the class. And so I took the peak of 1,050 parts for CO2 parts per million and used that to come up with a rough estimate of what ventilation is. And if you're not aware of it, the T.H. Chan School of Public Health, they have got a great this guide for helping. It was designed for schools, but really anybody could use it to help figure out their ventilation rates within their building. And it's a 5-step guide for doing it. And there's 4 different methods that they've spelled out for doing it. One of them is measuring CO2. So they have a nice little couple formulas in there. And so I modified the formula a little bit so I could kind of back work backwards through it to get to the ventilation levels. And so, making some assumptions on the school and the classroom, the area and the size, and the return air amounts. And I just went ahead and assumed 40% instead of going lower for relative humidity. The school did have a number of 11 filters. And then looking at the 6 students that were in there, as well as apparently, I think he had said that there might be some cases where they had up to 19 students in there. So looking at both of those situations. And so, but calculating it based on the dimensions, we get a rough estimate of about 102 CFM if in that particular case, and that's pretty low. It's way underventilated for that number of people. So that's the other thing to think about here is when, CO2 levels, you initially look at that 800 to 1,000, you think, oh, that's typical, right, for classrooms if it's meeting ASHRAE standards. Well, that's assuming a full occupancy. If it's a low occupancy situation, obviously you're not generating as much CO2, and so the CO2 should be lower in that particular situation. So that's why the estimate is around 100 in this particular case. So and so we looked at the baseline, everybody's mask wearing, and then I just threw in there what happens if you added 2 portable air cleaners. And so the probability of infection under looking at breathing and speaking to kind of to demarcate the 2 ends of potential threats here. So if the teacher's the one that's infected, and they're speaking a lot more than if the students are, but regardless, so that's the bracketing. So we've got under the baseline, just mask wearing, 8% to 27% probability of infection because we got such low ventilation. If we put if you ended up actually putting the 2 portable air cleaners in there, we can knock that down quite a bit, 3.8 to 13.7%. But if we take those percentages and multiply by the number of people that are actually in the space, you still, because, looking at the 6 students, right, you have it's only under the speaking conditions where you might potentially end up somebody coming out of there infected. Certainly, if you have more students, that increases. And then we do the same thing that we did for the other study. If we look at the county data to get a rough idea of what the community infection rate is, basically make an assumption of 1.75%. If we look at assuming 19 students plus a teacher, so probability of infection given that community spread rate 1 out of 20 would be almost 30%. 1 out of only 7, 6 kids and a teacher, that would only be 10%. So then you multiply those by your percentages, so you can see that those percentages come down quite a bit. The total risk, right? So this is the total risk if that community spread rate is actually that amount. And then your number of students infected obviously fall as well. And even if you assume, say it's really bad and it's a 5% infection rate, that would be pretty bad. But if it was, the percentages obviously, then the total risk goes up. But even with that 6 students, you do that de-densification, the chance is still relatively low that somebody's coming out of there infected under those particular conditions. And it's, especially if you put those portable air cleaners in there. All right. That's that case study.
Thanks. I think our next slide is the contact information. You can throw up there. So here are our email addresses and phone numbers. You can reach out with any additional questions if we don't cover it. This is scheduled till a quarter after the hour, so we do have some more time. So please get some questions in. We'll answer them as they come in, and then we can even model some other case studies too. So Hans asked here, and this is about risk, which is a difficult question for us to answer because we're not public health officials or epidemiologists. So it's hard to advise on what's risky enough to be safe or like have that discussion. But this is asking, would it not be true that if the risk is reduced to less than 1 person leaving infected based on the collective controls, that this would be generally deemed as an acceptable risk? And yeah, I think if less than 1 person is going to be infected that you're modeling, then that could be considered an acceptable risk. If it's 0.7 or 0.8, then that can be rounded up to 1. So that means 1 person is leaving sick or infected. Is that an acceptable risk? I don't know. I think that depends on what your goals are for your building occupants. And, you know, if you're okay with 1 student coming in sick and then a 2nd student leaving sick, then that's what you need to kind of determine as a building owner or with your clients.
And you need to have those discussions with your local community health officials. Don't try to make those determine, you know, what it, because making that assumption of what the community infection rate is difficult for lots of reasons. Part of it is because we're not testing enough, but I you know, those ranges that I'm using to bracket, you know, that's a wide range. And you know, you need to talk to somebody that knows what they're talking about to really have an understanding of which one of those community infection rate you should be using to multiply your probability of infection by. And none of us here are able to make that call. We don't. That's just not our area of expertise. So, you know, all we know is that that's probably a rough bracket of what the range of infection is in the community. But beyond that,
yeah,
other expertise is needed.
Next question here, and this is a good question. With a school with mixed ages, toddler to 3rd grade, older kids are more consistent mask wearers, how would the varying classroom risk factors relate to a building-wide risk with a shared mechanical ventilation system? Before you get to that, which Pete, it looks like you're about to answer, I do want to, we didn't dive into like what the tool actually looks like, and that's kind of the previous webinar that I'll send that link to in an email following this presentation. But you can model which percentage of people are wearing masks during the duration of the time. And I would suggest for a younger elementary group that it's probably not 100%. I know a few friends who are elementary school teachers, and they're constantly reminding the kids to put their masks back on. So maybe in that scenario, you do model a 50% or 70% to see that range of what infection would be with kids taking their masks off throughout the day. But Pete, I'll let you hit on that shared mechanical ventilation system.
Yeah, well, from a modeling standpoint, I would model the spaces differently, for one, because there's different characteristics happening there from a behavior standpoint. To Danny's point, you can model one with a much lower rate of mask wearing versus another one that's much higher. The fact that they share a common mechanical system, though, we're not seeing widespread outbreaks of this through a shared mechanical system from one, showing the virus moving from one space to another space. It's airborne, but most of the events that we've seen that are causing these super spreader events, it's in one space with systems that are churning that air through there, not pulling it back into an air handler. And Marcel, you've been following the research. I think there's a big difference between sort of finding RNA of the virus in a duct 16 feet away and then extrapolating that out to it moving throughout the building there. So do you have anything you want to add on that?
Yeah, I mean, that's right. And you can even just think of it, let's say even the virus did live and made it all the way back through the air handling unit and then back out. There's a dilution factor that occurs along with that as well. If they actually did make it, which the evidence at this point is not strong for. Certainly in the return duct work, they have found live or RNA within of the virus within the ductwork, and there's even been some indications of finding it at the air handling unit, but it's really small. It's small in terms of the amount, and by the time if it would actually make it back out into the spaces, it would be further diluted among all the spaces that the air gets distributed to, and much likelihood that it wouldn't necessarily be alive by that point. So yeah, the evidence that the main threat occurs within the space where the infected person is at. That's what the research at this point is showing.
Sorry, Marcel. I was just going to add, since the person that asked that, I think is referring to school environment too. One thing I would add, especially with the younger kiddos, we've looked at some preschool facilities that have issues with ventilation too, and that's where these portable HEPA filters, when we model those out, they have a really big impact. So if mask wearing and getting young kids to kind of consistently wear masks is a challenge, and we know that is, it might be worth taking a look at those portable HEPA filters for those types of spaces there. Even if you're not deploying it across the entire school building, maybe looking at those specific classrooms and seeing what it does could be important.
I don't see any additional questions or comments. So I don't know, Marcel, if you want to run through a planned case study, and then folks on the webinar, if you do have more questions or comments, please keep sharing and I'll keep interrupting with those questions.
So we could briefly, I've had some questions. Well, how do you know that the tool works? What have you done to validate it, I guess, which is a fair question. Besides the fact that the underlying models that this is based on has been around for a long time, and in other scenarios they have fact-checked it quite a bit, validated it, so we know it works from that standpoint. But we also we make our own assumptions when we put the tool together and stuff, and so it's still a valid question to let me go to. So I've done an initial run through looking at the Skagit Valley Chorale Superspreading event and running the data that's been collected on it through the tool to see, do we get something similar to what the reality was. Dr. Shelley Miller and her team actually did a study on this, and they spent time collecting all the data and information on the mechanical systems and interviewing people there. So we have some idea of what the parameters were that we could plug into the tool. And so we have square footage, ceiling height, which we know what the system design capabilities were, but we also know that during that event they didn't have it running because they'd run it beforehand. It was warm enough, and they were going to have enough people that they weren't worried about it being cold. And so by the time people were there, it was shut off. There were some some outside air entering the space. They estimated what the outside air was during that time. They figured it was around 339 CFM, but they did like a 50% low and high just to kind of to give them some room there. I did not see a 50% or a relative humidity estimate within the paper that they put out, nor in the supporting information, but based on the conditions there, I just assumed for that time of year, I just assumed that 50% that the system was off. you know, maybe since I figured it would be conservative in terms of the negative impact on people. So I started with that. We knew it was a MERV 11 filter, but because there was the system wasn't running, there was no recirculated air, it doesn't really matter for this analysis. Assumed, I ran it, they think it was probably a person that was shedding a lot of virus, but I ran it with a medium shedder just to compare the two. One infected person, there were 61 members present. Now for the exposure time, that was bracketed into 3 time periods. And they were predominantly seeing the whole time, each of these time periods. There was kind of 45 minutes where they were all together. There was 45 minutes where they were split up into 2 groups with there was no break between the first and second point. And then there was like a 10-minute break, and then they came back 50 minutes and sang again for most of that time. So I used a 2.3 hour total time estimate. And in terms of the people that were infected, there were 52 people that were sick. Only 32 people got tested. And so likely most of those 52 people were probably actually had COVID, but we don't know for sure because they weren't all tested. So they have to technically say it's between 32 and 52 people. So it's probably closer to 52 that were actually infected. So ran it through the tool. And so on the left is the medium shedder, and then on the right is the high shedder. And so the bracket, the 32 and the 52 bracket it, and then the kind of hunter green line here is the modeled outputs for each of these conditions. So this is the primary outside air CFM that they thought probably, but then 50% lower and higher on either end. And so on the medium shedder, we're within that bracketing range. If you know, it's probably towards the lower end of that, towards the 32 end for that 339 CFM. But they think this person was probably actually a high shedder, not medium or low shedder person. And so in that case, running it, we get 49 for 339 CFM, which is really close to that 52. So there's some more analysis we want to do here to compare it, but that, you know, from the initial output, that I feel pretty good with those initial results. And as we get more data from other events that we can compare, then we'll keep adding them to do those comparisons.
This was perfect, Marcel, because as you were talking, we did get a lot more questions in. And so I think that worked really well. And remind me, this was back in early March, like before.
Yes.
Yeah, okay.
Yeah, this was March.
So we have a question about adding UVGI, and he is assuming that it's for the room only, not duct. What is our opinion on its use in non-healthcare settings?
So upper UVGI, the upper room UVGI systems that irradiate a zone above the occupied space that are shielded from the occupants, those have been around since the 40s, 50s. Studies on them have been done since the 40s and 50s in different building environments, including schools. And we know that they are effective. They kill pathogens, including viruses like the coronavirus. They eliminate them pretty well. And so that is an option that you can consider, upper room UVGI systems. They're in the space where the infections are occurring, and so they can be an effective tool to use that. Now there are considerations. You know, there's a cost standpoint. There's some difficulties depending on the building in terms of the construction or installation of it. There are operational concerns that can present hazards to maintenance people. So that there's different things that you have to consider before you implement that. But it is effective. We've looked a little bit at applications at the air handling unit and in ducts. I haven't seen really good studies yet that demonstrate certainly not in ducts, and even in the air handling unit. The issue is the speed with which the virus travels through the irradiated zone in a duct, particularly in a duct, but even the air handling unit itself, in terms of how much virus is actually eliminated. That's one issue. The other is how much virus actually gets that far anyway, and needs to be killed, which also, particularly for at least for the coronavirus, and viruses in general, likely you're putting a lot of money into a situation where you may not necessarily need to even, there might not be a threat anyway that has to be addressed at that point. It's much more effective to deal with it in the space. And so I think we would recommend upper UVG. If you're going to do UVGI, we recommend the in-space stuff, the upper room systems, not there's the far UVC ambient fixture. That's a whole other question. But I think in-room is more effective than at the air handler or within the ductwork. Pete, do you have anything you want to add to that?
No, I think just in the non-healthcare setting part of that question. So, I mean, hospitals are generally the safest buildings that we have out there. Unfortunately, most or a lot of the other building types that we have, I mentioned schools are especially poorly ventilated, but offices are also on average not well ventilated. I think somewhere between 40 and 50% don't meet the standards for ventilation. So we've got a lot of existing building stuff we need to fix first, I would argue, before we get to some of these more exotic technologies. You know, let's retro commission systems and get them working properly before moving on to these more exotic things.
Great, thank you. One of the issues is understanding what happens to the viability of particles in mechanical ventilation processing. It would be helpful to factor this impact into models. Generally, I believe it's true that viability drops off profoundly at some point of desiccation, maybe needs some active viral particle testing methods. And I would like to point out that the tool that we're referring to that's free and online on our website really models kind of one room, and then within the tool you can put in how many rooms there are in the building to show what's happening in the building. But it's kind of under this assumption that we're looking at what's going on within this one space. So we're not really making a prediction on how the viral particles are moving through the mechanical ventilation, like the ductwork, if that makes sense.
Yeah, in a general sense, it's a simplified model. You assume a box. You can think of it in terms of the building system filtration. What it is, it's like it immediately leaves the box, goes through the filter, and then either it goes back into the room or somewhere else within the building. It's a simplified model of reality that other studies have shown actually does a relatively good job of predicting in general what's going on. And the other thing is that also speaks to the studies that we have seen don't show significant amounts of viral particles leaving the room, to the point where, I mean, if you're addressing the threat within the room, you're going to have less of an issue anyway, stuff going beyond the room. So that's why address the threat within the space. You'll have less of a likelihood to have to worry about things getting into the HVAC system beyond the space anyway, even if it does happen to be a problem, which the likelihood is low anyway.
We have a question about a metric version of the calculator, which you happen to have 3 people here who wish that the US operated in the metric systems.
I hear you. I wish it too. In fact, that was my, I wanted to do it in metric initially. I wanted to make people have to convert, but I got talked down. So
we'd love to go metric, yeah. But in an attempt to keep it simple, and especially for some of our users are facilities managers there, and they think in cubic feet per minute, and square feet and those sorts of things. So I would love in the future for us to add a little slider button that takes it from IP to SI. So hopefully we'll be able to do that in the future.
We have a question about eating lunch in a school, so where students are then taking off their masks. And this concern is moving to indoor lunches, and that his takeaway is that a small group of students in a dedicated classroom with a HEPA unit would be the lowest risk for a short mask break to eat. Is that accurate?
I'll I'll grab that one if you don't mind, because I've looked at that scenario before. It's really hard to generalize because in a lot of schools, actually their cafeteria is the safest space they have. One, it's the biggest box, which then allows for, even if there's a lot of people in there, there's maybe not as high a density. They're often mechanically ventilated, and that's a big thing. And in fact, when we look at the outside air rates in those systems, if you're putting in 50% of the people that it's designed for, you've got a lot of outside air coming into that. So if it's a well-designed system that's operating the way it was intended to, that could actually be the safest space in the building. And the duration is also pretty short too. When you're looking at like a lunch hour, or, you know, in the case of schools, it's usually even less than that.
18 minutes.
Yeah. And there is something to be said too, and this is just kind of coming to mind here. I haven't really thought about the modeling piece of this too, but leaving the classroom space for a little while. If you have a HEPA filter in there or a mechanical system, allowing that to sort of flush the space out while kids are out of there for a little while might, if there is a viral particle load in the space, that could actually allow for some reduction of that over time. So it's really tough to say, you know, do or do not use a cafeteria space without seeing the actual systems and numbers in place, but I certainly wouldn't write it off.
We have a question about how would you estimate someone's shedding level? Yeah, Marcel, I'm sure you want to take this.
So yeah, so there's two things with shedding, or the primary thing is at what point are they within their period of being infected, right? So, basically, what the research at this point says that the few days right before you start being symptomatic is likely when you're shedding the most of the coronavirus, and then maybe for a few days right after that. That window is really the, you know, on an individual basis, that window is the biggest for spreading the virus for in general. And then there is, for some reasons that we don't completely understand, certain people also seem to shed the virus. In general, they seem to shed viruses more than others, and that, we don't know, and it's hard. Can't really estimate that. I can't say there isn't any data that I know that you can get and say, okay, then you have this probability of somebody being a high infector. And so basically that's why we kind of run it with different. I usually start with medium, but then I might run a couple with the low or the high to just kind of see how it compares. It's likely you're going to have, at some point during the period that somebody is sick, they're likely shedding a higher load. But it's hard to know on any given basis when that is. So basically we would just recommend looking at running it with different scenarios and seeing what that is.
Perfect, thanks. And then our last question here, for any of your current or future case study buildings which you have used the calculator, is there on-site measuring of air quality, ventilation, and other variables, and a recording of infections to compare against the calculator with actual data, like Skagit, but using more certain data and a pre-infection calculator?
Can you read that question again, Danny? Sorry.
Yes. I think Pete, did you want to say something?
Yeah. So I think the question at its heart is, do we have ways of tracking the environmental conditions that are happening in the building, and then cross-referencing that against what's actually happening in the building in terms of infections? That would be an amazing study. That's not one that we have access to right now, especially not with HIPAA laws in the US and accessing people's health records there. It would be awesome to be able to have that type of data. Absent that, we're looking at things like the Skagit Valley Super spreading event is one. I've started to dive in a little bit, and I'm hoping we can get more data on this. A senior living facility that unfortunately led to 26 deaths in Joliet, Illinois. Senior living buildings in general are some of the worst conditions that, you know, I think we can draw up for spreading. And in this particular case, there was a maintenance worker that went into 40 rooms of residents while they were there, assembling furniture, talked about sort of the vigorous nature of putting this furniture together and the physical exertion of it. And 132 people were infected in that facility. So, you know, I think there will be data that comes out on that, and we're trying to kind of do some backwards looking detective work on that one as well. And I think that's what we'll continue to do to validate some of these results. Makes sense.
And something we didn't talk about, because I think in all of our case studies, the activity was light, but we do have in the estimator a way for you to change what the activity level is, light, medium, or heavy. And so if you're doing more physical activity, like in a gymnasium or moving furniture, you're more likely to shed more viral particles just because you're breathing heavier. So we can model that too, which we didn't really get into with any of these case studies. Well, thank you everyone for attending. Otherwise, you have our contact information, and we hope to hear from you soon. Thank you.
Thanks for joining us.